Okay, this is the last video for this course. And after watching this video, the rest of the time before the final exam will be just you review all the materials we learned this semester yourself. And the final exam would be on the finals week on Thursday. And I'll make an announcement about that. And before we talk about today's topic, and there are two handouts I uploaded on Canvas. One is the formula for the simple linear regression. The name of this handout is Chapter 9, Handout A. And you can find all the formulas for the simple linear regressions, including the intercept and a slope, and the inferences in ANOVA. And there is another handout called final exam formulas. So these formulas are mostly related to some special distributions, the calculations of expectation and variance, and there are some summaries of some formulas used in statistical inference. This is one sample inference and two sample inference. And we have the inferences for simple linear regression and chapter 9, multiple linear regression. And the chapter 7 is this part is what we are going to be talking about today. Okay, and check those out. So today we will be talking about chapter 3, 7.1, 7.2, and 7.4 in the textbook. It is an inference for unstructured multi-sample studies. So this is basically an extension of two-sample inference. But now we don't only have two samples, we have at least three samples. And to do this, we will use a model called a one-way ANOVA model. So this is the setup of the model. Suppose we have some response variables, y, and there is a covariate factor x. So usually in the one-way model, you will use the word factor. And the factor has several levels. We have R levels, and they are denoted as 1 to R. And there are Ni observations at level I. Okay. And the one-way ANOVA model, or sometimes called the one-way normal model, is this. Yij is a response for level in for the covariate associated with level I. And Yij is equal to mu I plus epsilon ij. The epsilon ij's are error terms, and they are normal, IID with mean 0 and the variance sigma squared. And mu I is the true mean response at level I of the factor. Okay. And J are the index for the observations at level I. So J goes from 1 to Ni because we have Ni observations at level I. Okay. So that means observations or level I has a mean mu I. Okay. So that means you have multiple samples. In this case, we have R levels for the covariate, and those R levels makes R samples, and each sample has a mean mu I. Each sample comes from a population with mean mu I. And another important thing for the one-way model is this assumption that the air turns are all ID normal with mean 0 and variance sigma squared. Note that the variance for OI are the same sigma squared. So that means variance for these are populations are the same. So this is the equal variance assumption in the two-sample inference. And this shows you shows you what the one-way model is. This is the formula. And in one-way model, we have R levels for the covariate. And these R levels gives us R samples from our populations. And these distributions, distribution 1, distribution 2, distribution 3 to distribution R, are those populations associated with level I. And mu1 to mu R are the means for these distributions. And remember, in the two-sample inference model, we also have the same graph. We have mu1 and mu2. These are the means for the two populations in the two-sample inference. And we assume that they have the same variance. And we do the inference for mu1 minus mu2. This is the thing we did before. Okay, here is an example of the one-way model. This is a concrete data. So we have 8 different formulas for a concrete, and we measure the compressive strength of these 8 different formulas. And this plot shows you the recorded strength in the y-axis for each level from 1 to 8 of the concrete formula. And because these 8 different formulas does not have any order, right? They are just 8 different formulas, so we give them a number from 1 to 8. So this order of numbers given to the formulas is actually meaningless. We should not do simple linear regression of the strength on the formula, right? So we will use a one-way model to do this. Instead of the simple linear regression, we will do this. So for the x, the covariate here is the formula index. And in a one-way model, we do not use this x as the explanatory variable in SLR. We are using this just as an indicator of a group. So if the response y is from the ith formula, then we have Yij equals mu I plus epsilon ij. The mu I is the mean strength of formula I. Okay, so here is the explanation of this model. I is the formula index. We have 8 formulas, so I from 1 to 8. And J is the index of specimen within the formula I group. Okay, so in this case, the X, the formula index serves as an indicator. It indicates which group the response is in. And so the name one-way model comes from that we only have one factor or one covariate, that gives you a certain number of levels. In this case, we only have one factor called formula index. So the formula index is a factor that tells us how many groups are there in the model. So there is only one of this factor in the model, and it's called a one-way model. And there are also two-way models. So in a two-way model, you have two different factors, and the combinations of these two factors will give us more different groups. Okay, that is the concrete example, and here is another example, the springs example. So there are 3 types of steel springs: type 1, type 2, and type 3. And we have some observations for each type of springs. For type 1, N1 is 7, N2 for type 2 is 6, and N3 is also 6. And we can make a side-by-side box plot for the 3 types of springs, and we can also do a scatter plot for these 3 types of springs, and we can see that it's like type 1, type 3 has a similar mean, and type 2 is bigger than type 1 and type 3. And since this type of springs as a covariate is also a factor that separates all the observations into 3 different groups. And we should also use a one-way ANOVA model for this kind of data set. The model is still this, and the Yij is the spring constant of spring type I, and the J's observation for the spring type I. And mu I is the true mean spring constant of type I, and I is the spring type. Okay, and it goes from 1 to 3. And J is the index of specimen within the ith group. So to fit this model, what we do is like this. we use the Yij hat to denote the fitted value corresponding to the observation Yij, and it is an estimate of the true mean response at factor level I in the sample unit J. And as you can see that because the Yij's expectation is always mu I. So if you are falling within the same level, if two of the regions are falling in the same level, since it's an estimation, it is an estimation of the mean. So Yj hat should all be equal to mu I hat. So the estimated response Yj does not depend on J. It's all the same if the I are the same. And they are all equal to yi dot bar. So what is y dot bar? Y dot bar is just the sample mean of the observations at level I. So we sum over yj for the j, for j from I to ni, and divide the summation with ni, the number of the observations at level I. And this is actually obtained by minimizing this loss function. So it's also a least squares problem. And the solution is just y dot bar. And so the residuals Eij are just Yij minus Yij hat, and Yj hat is mu I dot bar. So Eij is Yij minus mu I dot bar. So one thing to mention is that this dot here actually means that we are doing the average over J, because the I is fixed here. The thing got averaged is the index J. And this is the fitted result of the concrete example. We have 8 formulas, and altogether there are 24 observations. And we got the fitted value. Yj hat is equal to yi y dot bar. And you can see that for concrete formula 1, the fitted values are the same. And for 2, they're also the same. And for formula 8, the fitted values are also the same. But the residuals are not necessarily the same, because the response are not the same for all the observations in the same level. And you can do the model diagnostic also using the residual plot. So the residual plot is the residual against the fitted strength Yj hat, also called Yi bar. So in this plot, you can see that if you make a reference line y equals 0, you can see that the points are scattered around this line. So it's evenly distributed around this line. So this is good. And we can see that the spread for each level are almost the same. So that also indicates that the equivariance assumptions is plausible. And to check the normal distribution, because we assume that the epsilon ij in the model should be with mean zero variance sigma squared. Okay, so we can also plot the normal QQ plot of the residuals, and for the concrete data, we can see that all the points in the QQ plots are falling around a straight line. So that is also good. That means the residuals are almost normally distributed. And our normal assumptions in the model is also plausible. Okay. So one important thing in the one-way model is the variance estimation, because we don't know the sigma in this model. And to do the inference, we will always need an estimation of the variance. And to do that, we did the same thing as we did in the two-sample inference. In the two-sample inference, when we assume the equivariance assumption, we use the pooled sample variance. So here we also use the pooled sample variance. The pooled sample variance is done by this. You first compute the sample variance for each factor level. So Si squared is the sample variance for the level I, and it is Yj minus, this should be Yi dot bar, there's no J here. So Yj minus Y dot bar squared, and sum it up, divided by Ni minus 1. So this is just the sample variance for the ith group. And you can compute the pooled sample variance in this way. So it is n1 minus 1 times s1 squared plus n2 minus 2 times s2 squared, all the way to nr minus 1 times sr squared, and divided by n minus r. So n minus r is just n1 minus 1 plus n2 minus 2 plus nr minus r. Okay, so n here is n1 plus n2 plus nr, the total sample size. And R is number of groups or number of levels. The pooled sample standard deviation is just the square root of the pooled sample variance. And here is another formula. So this Yj minus Yi bar is just the residual Eij, right? So we also showed that the denominator is n minus r. That means the sample variance, the pooled sample variance is just the sum of squares of the residuals divided by n minus r. Okay. And it turns out that with this result, we find that the expected value of the SP squared, the pooled sample variance, is sigma squared. And n minus r over sigma squared times SP squared is has a chi-squared distribution with degrees of freedom at minus r. So because of this, the 1 minus alpha confidence interval is like this. Why? So we know that n minus r over sigma squared is p squared, has a chi-squared distribution. So this thing this probability, because this is just a chi-squared random variable. So this probability is the probability that this random variable is between the alpha over 2 quantile and 1 minus alpha over 2 quantile. This is chi-squared alpha over 2, and this is chi-squared 1 minus alpha 2, right? So this tells you that this area is 1 minus alpha, and this area is also 1 minus alpha. So the area in between is 1 minus alpha, right? So this probability would be 1 minus alpha. So if you rewrite this in inequality, you get sigma squared is between n minus r over chi squared and minus r alpha over 2 times sp squared and n minus r chi squared and minus r 1 minus alpha over 2 sp squared. This is just written from this inequality. And that gives you the two ends of the 1 minus alpha confidence interval. Okay. So again, for the concrete data example, we calculated the sample standard deviations for each level, and the pooled sample variance is 338,213. And the square root of that is the sample standard pooled sample standard deviation, which is 581.6. So this one is so for this data, all the groups have 3 observations. So you can take the 2 out and have a more convenient summation. And the confidence interval for the pooled sample standard deviation, should be, yeah, right, the pooled sample standard deviation can be calculated as following. So the first total sample size, n, is 24, and we have 8 levels, 8 formulas, and so R is 8, so n minus R is 16. And so for the 95% confidence, so for the 90% two-sided confidence interval, we will need chi-squared n minus r 1 minus alpha over 2, right? And chi-squared n minus r alpha over 2. So in this case, alpha is 1 minus 0.9, which is 0.1. So 1 minus alpha over 2 is then 0.95, and alpha over 2 is 0.05. So we obtain these two quantiles of chi-square distribution. And plugging the formula for the two-sided confidence interval for sigma squared. M minus R times is p squared, and in the denominator we have these two quantiles, and it is this interval. And the 90% confidence interval for sigma is then transforming these two endpoints of the confidence interval for sigma squared. You take the square root of these two, and you got the 90% confidence interval for the standard deviation. So it is from 453.7 to 824.5. And we are 9% confident that the true overall standard deviation of the compressive strength of concrete within the factor levels is between 453.7 to 824.5. Okay, that is the estimation for the standard deviation. And we also have the standardized residuals, as in the simple linear regression and multiple linear regression. Although the epsilon ij's are IID, which mean zeros are variance sigma squared, but the EIJ's does not have a constant variance. It changes as the levels changes. And the standardized residual for the one-way ANOVA model is this form. Epsilon EIJ star is the standardized residual, and it is EIJ divided by SP times the square root of n9 minus 1 over n9. So from here you can also see that we are dividing the same number for the residuals belonging to the same level. So the denominator does not depend on J. Okay. Although the variances are different for EIJ, but EIJ, the variance for EIJ when I is fixed are always the same. And actually the variance of EIJ is just sigma squared times n9 minus 1 over okay. So for level I, the variance is determined by this. And if the ni's are all the same for all the groups, then the variances of EIJ are actually all the same. So in this case, you can just use the raw residuals instead of the standardized residuals because they are essentially the same because the variances are the same. And next thing is the inference for the one-way ANOVA model. So remember in the in two sample model, let's write it here. In two sample inference, so one thing we are interested in is this H naught mu1 equals mu2, and HA is mu1 is not equal to mu2. So we are interested in whether the two means for these two populations are the same. And in the one-way ANOVA model, we are also particularly interested in this hypothesis testing. Whether all the means for all the levels. So there are R levels or R groups. Whether all means mu1 to mu_r are all the same or the opposite. Not all of them are the same. At least the two of them are different. Okay, so here's how we did the test. So the test statistic used here is an F test statistic. It is very similar to what we have in the ANOVA for the simple linear regression and multiple linear regression. We are using MSR divided by MSE, and MSR is SSR divided by R minus 1, and MSE is the MSE divided by M minus R. Okay. Here is N is the number of observations, that is N1 plus N2 plus NR, the total sample size. And R is the number of levels or the number of groups. There are means for you to compare. And SSR is this yj hat minus yi dot dot bar. So what is yi dot dot bar? Y dot dot bar is just y bar. This is just summation of I and j, yj n divided by n. Okay, this is just simply the sample variance of all the response. So the formula is the same as the simple linear regression and multiple linear regression. And because in the ANOVA model, the yj hat is yi dot bar, so SSR is y dot bar minus yi dot dot bar, and the square of that and sum it up. The SSE is yj minus yj hat squared and the summation. And since yj hat is yi dot bar, so for the ANOVA model, so for the one-way ANOVA model, SSE is yj minus yi dot bar squared, and then the summation of that. Now, assuming that H0 is true and the one-way ANOVA model is true, the Epsilon ij's are ID normal 0 sigma squared. So that means the variances are all the same for these R groups. Then this test statistic F have an F distribution with degrees freedom R minus 1 and N minus R. And we will reject H0 if the F test statistic is large. We will reject it when F is greater than the 1 minus alpha quantile at significance level alpha. So these are the same as the ANOVA test for the simple linear regression. We always reject the null when F is large. Okay, so we can compute the observed F using data. So to do that, we can construct an ANOVA table. So the ANOVA table is like this. So there is a source column. The source is, and the first row is from the covariate or the factor. It is associated with the SSR, and the degree of freedom is R minus 1. MSR is SSR divided by R minus 1. and you calculate the SSE, and the degrees freedom is n minus r, and the MSE is SSE divided by n minus r. Then the F test statistic is MSR over MSE. And then if you observed an F statistic that is larger than this critical value, we just reject H0, or we can use the p-value. The p-value is the probability that this fr minus 1 and minus r random variable is larger than the observed F test statistic. Okay. If the p-value is small, then we also reject H0. The last step would be the conclusion in layman's term. Okay, so in a concrete example, we want to do this test if all the compressive strength of these 8 different formulas are the same. So we do this test. The null hypothesis is that they are all the same, and the alternative is that not all are equal. We are doing the tests for the significance level alpha equals 0.05. The test statistic is R divided by R minus 1 over SSE divided by n minus R. So R minus 1 is 8 minus 1, 7, and n minus R is 24, because the total sample size is 24. 24 minus 8, which is 16. And assuming that H0 is true and the model is true, epsilon ij's are ideally with mean 0 and the sigma squared. Then the test statistic has a distribution. So in this case, it is f r minus 1 is 7 and n minus r is 16. We will reject H0 if f is larger than f7, 16, and the 0.95 quantile of this distribution. The number is 2.66. This is from table B6 in the textbook. Okay, so to calculate the observed F test statistic, we first calculate SST and SSE. So SST is the total sum of squares, and with SST and SSE, the SSR is just SST minus SSE. So this relationship is given in the simple linear regression and multiple linear regression lectures. And the total sum of squares is the Yij minus mu y dot bar. So it is just Yij minus the sample mean of all the y's. And the total sum of squares is this number. And to calculate SSE, we can do this because SP squared is SSE divided by n minus r. So if we know that SP squared is this, then SSE is just n minus r times SP squared. And SSE is this. So the SSR is just SST minus SSE. And this is SSR. Okay, so we have the SSR, SSE, And the degrees freedom for SSR is 7 because we have 8 groups, and M minus R is the degrees freedom of the SSE, which is 16. And we calculate the MS for each of these. The ratio of these two MS is 20. And we find that observed F20 is larger than this critical value, so we reject H0 and conclude HA. That means there is enough evidence to conclude that the compressive strength of the concrete varies with formulas. Okay, and this can also be clearly seen in this plot. Right? So for different formulas, clearly we see that the y has different means. They are not the same. Okay. And here's another example. The railroad rails. So the response measured is the mechanical wave travel time for these 6 kinds of rails. And there are 3 observations for each level of rails. Again, we use a one-way model. Yj is observe the travel time of the wave in excess of 26.1 millisecond. So this is just the measurement for rail I and wave J of the rail I. Excuse me. And mu I is the true mean travel time. The true mean travel time in excess of 26.1 millisecond of wave through rail I. Okay. And we can make a scatter plot of this travel times for each level of the rails. And from this plot, we see that the means should be different. And before we do the testing, it's better for us to check whether the normal assumption and the equivariance assumptions are met, right? Because we assume that epsilon ij are normal, which means 0 and a sigma squared. So we need to check normality, right? Because we have a normal assumption here. And we also need to check the equal variance assumption, right? Because we are assuming for all the i's or all different level, the variances are all the same. They are equal to sigma squared. And to do that, we can use the normal quantile plot. And the way is that you make the normal QQ plot for all the observations in these 6 groups on the same plot. And you want to check whether for each group the dots are closely around a straight line. And in this case, you can see that there are only 3 observations for each group. So and you can see that these 3 dots are almost on a straight line for all these 8 groups. And the next thing you want to do is to check whether these straight lines are parallel or not. So parallel means equal variance. Okay, and if they're not parallel, so might not the variance might not be equal. In this railroads example, you can see that these 3 lines are almost equal, and these 3 lines are like parallel, but these 3 and these 3 might not be having the same variance. So it's like the assumption is kind of violated. Um, but we will still move forward with this one-way model because in the normal quantum plot, if they're not parallel, that means that the assumptions just might not be true, but it still might be true. The reason is that we only have 3 observations for each group. So if you get more observations, it's likely that the normal QQ plot will give you some parallel straight lines. So this is very likely due to the lack of data. Okay, and you can also plot the residual by predicted plot, and in this residual by predicted plot, you can see that the residues are evenly distributed around the line y equals 0. So this is good, but the problem is that the spread for each level are not almost the same. So this is the same thing indicated by the normal QQ plot that the equal variance assumption might not be true. But since we only have 3 observations for each group, so we can still assume that the variances are the same. So this violation might only be due to the lack of data. Okay. And in this course, you don't need to worry about the unequal variances case because that is not covered in this course. And the next thing is that we also want to check the number assumption using a normal QQ plot. So this is the normal QQ plot of the residuals because you assume that the epsilon ij's should be normal with mean zero and variance sigma squared. So the residuals eij should also have an approximate normal distribution. And from this QQ plot, you can see that there is also kind of violation of the normal assumption. But since the dots these points, so these points are all within this confidence band. So these two lines are the confidence intervals. And if you see in a normal QQ plot that all the dots are within these 2 lines, 2 limits, then this violation should not be a severe problem. Okay, so we can still assume that the normal assumption is true. Okay, and so after checking all the assumptions, we can just do the formal hypothesis testing. The null hypothesis is that mu1, mu2, mu6 are all equal, and the alternative is that they are not all equal. The significance level alpha is 0.05. The F test statistic is SSR over 5 because we have 6 groups, and SSE over 12. So that is n minus r. N is 18 and r is 6. Okay, and assume that H naught is true and the model is also true. The epsilon ij's are ID normal with mean mu and sigma variance sigma squared. Then we have fr minus 1 and minus r. So in this case, it is f5, 12. And we will reject f if f is large. And we use the 0.95 quantile because the significance level alpha is 0.05. That is 3.11. Okay. So we will use jump to fit this ANOVA, a one-way ANOVA model. So we first need to load the data into jump and fit the travel time on rail and make sure the rail variable is a factor. So in the column, if you check the column assumption, the modeling type is should be nominal here. Okay. And there's going to be another video for doing this in jump, so check that video out. And in the output, you can find this ANOVA table. In this ANOVA table, you have the SSR, and this is SSE, and this is MSR, and this is MSE. And you got observed F statistic. It is 115.1814, and that is greater than 3.11, the critical value. So we will reject H naught and conclude the alternative. And you can also look at the p-value here. The p-value is a small number that is less than 0.0001. So you can also reject H naught because the p-value is so small, right? And then the conclusion is that there is enough evidence that the true mean excess travel time of waves along the rails depends on the rail. That means for different rails, the travel time are different. The means are not all the same. It depends on the rail. Okay, the last thing is the confidence interval for a linear combination of means. So in the one-way ANOVA model, we have multiple samples from multiple populations, and these populations have means from mu1 to mu-r, and we are interested in comparing these means. And there are many ways to compare these means. You can simply find a mean for group 1. So maybe we are just interested in the mean of group 1. Then I want to have a confidence interval for mu1. And if I want to compare the group 1 and group 2, then I want to make a confidence interval for mu1 minus mu2. Okay? And I can also make a confidence interval of the average of mu1 and mu2 minus mu3. That compares the average of the mean of group 1 and group 2 with the mean of group 3. And then we will construct a confidence interval for the linear combination of these means. Because there is a lot of possibilities, so this is general formula. And linear combination, we denoted it as L. L is equal to C1 times mu1 plus C2 times mu2 plus CR times mu r. Okay, so for mu1, then C1 is 1 and C2 to CR is 0. And for mu1 minus mu2, then C1 is 1, C2 is minus 1, and 0 for others. Okay, and since the estimate for mu I, because we estimate mu I using the mu I dot bar, then the estimate of L is simply you replacing mu I with mu I dot bar. Then we use L hat to denote the estimate of L. L hat is C1 times Y1 dot bar plus C2 times Y2 dot bar plus CR times YR dot bar. And under the one-way normal model, we have this result. The mu I dot bar is because the mu I, the Yij are normally distributed with mean mu I and variance sigma squared. This is based on the one-way normal model. So mu I dot bar is just a numerator variable with mean mu I and variance sigma squared over ni. Okay. Then with that, you know that the L hat has a mean C1 times mu1 plus C2 times mu2 plus CR times mu r, right? Because the mu I dot bars has a mean mu I, and the mean of L hat is just this. And the variance is sigma squared times C1 squared over N1 plus C2 squared over N2 plus CR squared over NR, right? Then you know that because this thing is nothing but the L, the unknown true linear combination. And then we know that by standardizing it, we have the L hat minus L divided by the standard deviation, which is sigma, times square root of this thing as a standard normal distribution. But the sigma is unknown here, so we replace this sigma with the pooled sample standard deviation. Then this thing will have a t distribution with a minus r degrees of freedom. Therefore, the two-sided 1 minus alpha confidence interval is this. It is L hat plus minus. The quantile used here is 1 minus alpha over 2 quantile for the two-sided confidence interval. And the distribution is t and minus r. Okay? And this part is just the standard error or sample standard deviation of L hat, right? This denominator is the sample standard deviation of L hat. It is SP times this big thing under the square root. And the one-sided confidence intervals are analogous, right? Or like for the lower one-side confidence interval, you will use n minus r and 1 minus alpha, the 1 minus alpha quantile of the Tn minus r distribution. And you have the center error of L hat. Okay, so here is again another example. We use the railroad rails data, and we'll be doing the following. We will construct a 95% two-sided confidence interval for mu1, and 95% two-sided confidence interval for mu1 minus mu2, and 95% lower confidence bond. So it is a one-sided confidence interval for mu3 minus mu5, and a 90% two-sided confidence interval for 1/2 times mu1 plus mu2 minus mu3. Okay, and we will be using the jump output. In the jump output, you have these two tables. The least squares mean table gives you the estimates of mu's. So these 6 means are just the yi dot bar. And the summary of fit table, you got the pooled sample standard deviation. This is SP. And for the first example, we will be using Tn minus 1 minus f over 2. So n minus r here is 18 minus 6, 12. And 1 minus alpha over 2 is 1 minus 0.05 over 2, which is 0.975. So we need T12, 0.975. And in the table B4, it is 2.1779. Okay. And then the y1 dot bar plus or minus. The y1 dot bar is the estimate of mu1 plus or minus this quantile times SP times the square root of 1 squared over 3, right? Because in this case, C1 is 1 and C2 to C6 are 0, and N1 is 3, right? And then you got the confidence interval from 48.941 to 59.059. And the conclusion is that we are 95% confident that the mean mechanical wave travel time for real one, actually the excessive mechanical wave travel time for real one, is any number between these 2 nanoseconds. Okay, and next, the two-sided confidence interval for mu1 minus mu2. And we use y1 dot bar minus y2 dot bar here, because it is mu1 hat minus mu2 hat. And again, we use the same quantile because it's a 95 two-sided quantile, no confidence interval. And we have SP times square root of 1 squared over 3 plus minus 1 squared over 3. This is because we have C1 equals 1 and C2 equals negative 1 in this case, right? And the rest are 0. And N1 is equal to N2 and equals 3. So plug in all the numbers. So these two are obtained in the jump output. This is from table before, and this also from the jump output. Then the number in the square root is 2 over 3. Then you get this confidence interval. It's 15.179 to 29.487. So we are 95% confident that the mean mechanical wave travel time for real 1 is longer than that of real 2, because the confidence interval is positive, by any number between 15.179 and 20.487 nanoseconds. And the last, and the third one, 95 two-sided, one-sided confidence interval for mu3 minus mu5. So because it is a one-sided confidence interval, the quantile we use is the 1 minus alpha quantile. So it should be the 0.95 quantile of T12, and it is equal to 1.782. And the lower 95% confidence bound is then this is mu3 dot bar minus mu5 dot bar. This is mu3 hat minus mu5 hat minus the quantile times SP and the square root of 1 squared over 3 plus minus 1 squared over 3. So this is because you have C3 equals C5, C3 equals 1, C5 is also equal to, C5 is equal to negative 1, and 0 for the other. And N3 is equal to N5 is equal to 3. Okay, and you can find these two values in the jump output. This is from table before, and SP is also from the jump output, and from the square root you have 2 over 3. Then you got 28.816. This is the 95 lower confidence bound for mu3 minus mu5. And then we are 95% confident that the mean mechanical wave travel time for real 3 is longer than that of real 5 by at least 28.816 nanoseconds. Okay. And the last one. This is the 90% two-sided confidence interval. So the quantile we used here is also 1 minus alpha over 2 quantile, and since it's a 90% confidence interval, then 1 minus alpha over 2 is 1 minus 0.1 over 2, which is 0.95. And the number is 1.782. So in this case, because it is mu 1 over 2, mu 1 plus mu 2 minus mu 3, so it is 1 over 2 mu 1 plus 1 over 2 mu 2 minus mu 3. So you know that C1 is 1 over 2, C2 is 1 over 2, and C3 is minus 1. Okay. This is L hat. L hat is just replacing mu1, mu2, mu3 with mu1 dot bar, mu2, 3, mu2 dot bar, and y1 dot bar, y2 mu bar, and y3 dot bar. We use the T12.95 quantile, SP times under the square root, we have 1 over 2 squared over 3, and plus 1 over 2 squared over 3, and negative 1 squared over 3. So this is 1/4 plus 1/4 plus 1 divided by 3, then that is 1/2 plus 1, that is 3/2 divided by 3, then it is 1/2. So under the square root, we have a 1/2. And this y1 dot bar, y2 dot bar, and y3 dot bar can be found in the jump output. This is the quanta, and SP is 4.021. Then the 90% confidence interval for this thing is negative 46.901 to negative 36.767. And then we are 95% confident that the average of the mean mechanical wave travel time for real 1 and real 2 so this is just 1/2 times mu1 plus mu2 is shorter than the mean mechanical wave travel time of real 3 by any number between these 46.901 and 36.767. Okay, so you can find that for all these 4 confidence intervals, you are always using the pooled. Always use the pooled sample standard deviation and the T and minus R distribution for the quanta. Okay. Although for these 3, so for this one, it's like you are only doing confidence interval for group 1, but you still use the pooled sample standard deviation and T and minus R. Okay. And for these 2, it's different from the 2 sample inference because in the one-way model, you always use the pooled sample standard deviation, and because you use the pooled sample standard deviation, you are estimating the standard deviation with the information you found in all the R groups. So you need to use a T distribution with a minus R degrees of freedom. Okay. So always use the SP and the Tm minus R for the one-way model. Okay. It's different from one sample or 2 sample inference. Yeah, if you remember that for the 1 sample inference, we are using the Tn minus 1. And for the 2 sample inference, we also use the pooled sample standard deviation. But we used n1 plus n2 minus 2. Okay. But in the one-way model, you always use a pooled sample standard deviation, no matter what kind of linear combination it is. And we use the Tn minus R as our reference distribution. Okay. And that is all for this course. Thanks for taking section 4. And the rest of the time is for you to review what you learned in this course. So there will be no more videos. Okay, and the announcement of the for the final exam will be given 1 week prior to the exam. That's all.